Okay, today I am talking about section 4.4. This is part 4 of that section. In this particular case, we're looking at integral defined functions, and we're looking at them graphically. Okay, so the first thing is that we're given this function f, the graph of that function, and it is continuous on a closed interval. So this does not go, all reals or anything like this. It begins and ends from -2 to 3, and that's it. The function that we're generally going to be asking questions about here is g of x. Now this is not g of x, so please don't be confused. G of x is what we call an integral defined function. We've seen these a little bit already in the last video, but we worked with them algebraically. Now we're working with them graphically. So take a look. G of x is equal to 0 to x of f of t dt. So essentially, g of x is based off of different areas related to f, and this is something we're going to work through today. As I talked about last time, this is our actual variable, our independent variable. You can think of it as the active variable. It's a thing that changes. The t here is what we call a dummy variable. That's sort of like a placeholder. So when I write, functions, I don't want to use t's, I want to use the g of x or f of x. T is sort of that placeholder, as I talked about in the last video. Does cause a little bit of confusion, so hopefully we can work through that with some time. Okay, so let's talk about this and what this means. So we'll just start off by just finding values of g, and then we'll move on from there. So the first thing is, if I say g of 2, what I'm saying is I'm plugging a 2 in for the x here. So like I said, the limit is actually the active variable. So g of 2 means I'm starting at 0 and I'm going to 2, and that's f of t dt. So essentially, I'm just integrating from 0 to 2 of f of t dt. Now, when I look at something like this, 0 to 2, we know that areas above will be added, areas below will be subtracted. Now, these are typically going to be geometric shapes. So for instance, here we just have the area of a triangle. So we're talking about all this area in here. So that will equal 1/2 times 2, and then the height is 2, so that gives us 2. Okay, so the area, or excuse me, g of 2 is equal to 2 because it's integrating from 0 to 2. All right, let's go on to g of 3. Not much different here, except when the area drops below, or the function drops below, we're talking about the area between the x-axis and the function, but that's going to be a negative value instead of a positive value. So we're still integrating from 0 to 2. We already know that's positive 2. We don't have to redo that. But then what we're doing is we're subtracting this little area down here. Oh, by the way, hopefully this is clear. These are two straight lines, line segments, I should say. And these are all, one increment here. So for instance, that point 0, 2. This point is -2, -2. Okay. So anyways, we have this area, which is 2. And then because this drops below, we're subtracting that, which is 1/2 times 1 times 1. So what we get is 2 minus 1/2, which is 3/2, or if you want, you can call it 1.5. It really doesn't make a difference here. All right. Now, so let me just point something out to you. In both of these cases, we were going 0 to something that was to the right of that point here at 0. The rest of these switch, okay? So we're going g of -1. So what that means, I'm integrating from 0 to -1 of f of t dt. So as we talked about with our properties, we don't want this written from greater to least. We want this from least to greatest. So that means I'm going to negate this, and now I can flip this, okay? Actually, let's clear out some room here. Okay. So I'm still doing the integral, but we have the negative out front. Okay, and we'll talk about what that means. So we're doing from -1 to 0. So we have that negative out front. Once again, we're talking about triangles. 1/2 times the base is 1. That's 2. So what we get here is -2. So g of -1 is -2. And we'll talk more about a way to look at this in a second. And then finally, that leaves us with the g of -2, and we're getting the same relationship again. We're going from 0 to -2, of f of t dt, which is equal to negative 2 to 0 of f of t dt. So I'm doing a negative of, and then I'm doing the area below. Okay, so that's going to be a negative, right? So that'll be negative 1/2 1 times 2, right? The area of that triangle. And then this is going to be plus, and then 1/2. Well, we already did that one. That one is 2. The area of that is 2. No, I'm sorry. This is negative 1. My bad. So let's go back and fix that. Of course, that's negative 1. Sorry about that. Anyways, so then we're adding that 1 here for that area above. But what ends up happening is we get negative 1/2 plus positive 1/2. So we don't call that negative 0. That's just equal to 0. But the thing we want to take note of here is that, and this is where it gets a little confusing. And what I would say is when you see these integral defined functions, and they're not always 0, you want to pay attention what that bottom limit is. Whatever that bottom limit is, I would draw a vertical line. As we evaluate values of g to the right of that vertical line, whatever that value is, we treat integrals like we normally do. Areas above will get added, areas below will get subtracted, like always. The thing is, when we switch, okay, when we go to the left of that 0 point, it switches. So areas above will now be subtracted, right? Remember, we got a negative 1 here, and areas below will actually be added. So here we had the negative 1, and then this was a positive 1, which ended up giving me the 0. I will tell you that if you need, if you get confused, you can write this stuff out. But with these types of problems, this is one of those rare cases where there's no justification needed. You can go right to the value. So if you just keep that idea in mind, that wherever that value is, it could be any of the values in here. It could be 1, could be 2. As we move to the right, areas above will be added, areas below will be subtracted. As we move to the left, they actually switch. The areas above will be subtracted, areas below will be added. Okay, so that's how we're going to evaluate the actual g. Now we're going to get to questions we see in the past. So we're going to answer when is g increasing, decreasing, concave up, concave down, things of that nature. So let's get to those. Okay, so parts B and C, we're returning to something we've actually talked about before. This actually is very, very much the same as when we were giving a derivative graph and then we were answering questions about the original function, which I'll talk about here. So in part B, we're doing intervals of increasing and decreasing. In part C, we're doing intervals of concave up and concave down. So what we want to realize is that as soon as I see this notation, okay, and we talked about this is the fundamental theorem of calculus, we want the derivative of this. So what I know is g prime of x, the derivative of g, is actually equal f of x. So if you remember, we were working through these algebraically, we were asked these types of questions. As long as this is any constant with x on top, if we take the derivative, we basically, what ends up happening, as we talked about, and this is the fundamental theorem of calculus, the most important idea that we work with. The integral and the derivative are these inverse functions. It's like multiplication and division. If we multiply by 2 and then divide by 2, we're back to whatever that original number is. So with that in mind, we're integrating f, and then we're differentiating it. So essentially, the derivative of g is f. So from here, this becomes just like those questions we did a week or two ago, where you were given a graph of the derivative and you were asking questions about g. It's really no different there. So a lot of this from here on out is review. Notice, when we take the derivative, that bottom constant doesn't matter at all. That only matters when I'm doing values of g. People get confused by that, but it doesn't matter because that's just going to generate a constant. When I take that derivative, that constant will go to 0 anyway, so it doesn't matter what that bottom limit is. Okay, now we have this. I would write this. And so from here on out, as soon as you see these integral defined functions, I would write two things. I would write a vertical line wherever that bottom limit is for when you evaluate g. And the next thing I would do is I would write the derivative of g is equal f. Okay, find intervals where g is increasing and decreasing. So now we recognize that this thing is the derivative. It's very straightforward. When the derivative is positive, g will be increasing. So we're increasing whenever the g prime is greater than 0. So that is going to be -1 to 2, and that is because g prime, which is equal to f, is greater than 0, and that is it. We are done with increasing. Decreasing, okay? Decreasing, we have two places where the derivative is less than 0. So that's going to be -2 to -1, and then 2 to 3, and that is because g prime is equal to f is less than 0. And you do have to have that justification. This is a little redundant. I keep writing g prime is equal to f. Technically, once we make this connection, you could use either one. You could say g prime is greater than 0. You could say f is greater than 0. Once we say they're equal, we could use those interchangeably. I'll write them both because both are acceptable. Okay, so increasing -1 to 2, decreasing -2 to -1, and then decreasing from 2 to 3. Okay, find x intervals where g is concave up and concave down. So we have to keep this straight again. It's been a little while since we talked about this. So how do we know that g is concave up or down? We look at its double derivative, g double prime. Now what we have access to is g prime. So g double prime is the derivative of that, okay? So what that means, right, the derivative of a function tells me whether it's increasing or decreasing. So when g prime is increasing, it means my double derivative is positive, which means g is concave up. I know it's a lot. And then on the other side of that, when g prime is decreasing, that means that g double prime is negative, which means that we are concave down. Okay, so let's go ahead and write that up. Concave up. So we are concave up when g prime is increasing. So that's going to be from -2 to 0, and we would say because g prime, which is equal to f, is increasing. As we talked about before, if you do use g double prime here, say g double prime is greater than 0, you're actually saying the same thing, but typically we want to talk about the graph that's in front of us, but I wouldn't take off for that. Concave down, that would be from 0 to 3, and that is because g prime, which is equal to f, is decreasing. Okay. Also, let me mention, I'm not talking about this here, but this then goes into things like, where do I have inflection points? Well, I'm going to have an inflection point at x equals 0. That is because our g prime is going from increasing to decreasing. So that's going to be our only inflection point. I'm not asking that specifically here, but we will get it to the relative max and mins and critical points. So let's get to that. Okay, so part D, find all critical points, then identify each as a relative max, min, or neither. So first critical points, we don't have to think about what's happening here other than we're looking for when g prime equal f is equal to 0. So we have two critical points here, and our critical points are at x equals -1 and x equals 2. And that is because g prime, which is equal to f, is equal to 0. Okay, so critical points. Now, we want to identify each. So keep in mind that if my derivative goes from negative to positive, right, that means that I'm going from decreasing to increasing. That's going to be a min. So I have a relative min at x equals -1. We've already said that it equals 0, so we don't have to say that again. If we were going right to the relative min, I wouldn't want to identify it as a critical point. So g prime, which is equal to f, goes negative to positive. Okay, and then of course that means then at x equals 2, we have a relative maximum. So we have a relative max. This marker is not great. Ah, that's better. So relative max at x equals 2, and that is because g prime, which is equal f, goes positive to negative. And of course, We don't have this here, but if we see a critical point where it doesn't change sign, that would be neither. Okay, so really, B through D so far is really review for when we're given a derivative function and asked about the original function. Part E is also review. We're going to sketch G. The difference between this and what we did before is, if you remember what we did before, is I gave you 1 point to sort of lock it in, and then we just went by the general shape. However, now we have all those values from part A. So we're going to start with all those values from part A, and then we'll look at the increasing, decreasing, concave up, concave down. Okay, so let's do that. Okay, so now we're going to sketch G, -2 to 3. We're going to start off part A. We'll just plot all those points we did in part A. So I'm just going to go through that. G of 2 we had as 2. G of 3 we had as 3/2 or 1.5. Okay. G of -1. First, G of 0 we know is 0 because that's where it goes 0 to 0. G of -1 is -1. Okay. And then G of -2 is -2. Now, I don't think I explicitly mentioned that, but just remember, wherever that point is, G of 0, whatever that value is, that will be where it zeroes out, because that property of going the same number to the same number, that's always going to be 0. So whatever that value is, or if we draw that vertical line, the original function will be 0. Okay, so this gives us a good look at what this graph is going to look like. It's a little bit redundant to talk about when it's increasing or decreasing, but let's go ahead and do that. Oh, wait a second. Something went wrong here. Oh, of course. G of -2 is not -2. Not -2, it's 0. Didn't make any sense. Okay, so let's go ahead and take a look at this. As I did before, I keep track of 2 things dealing with the shape. I keep track of when this thing's increasing or decreasing, which we really get from these values we did, and we're going to keep track of concavity. I tend to keep track of whether it's increasing or decreasing above, so let's go ahead and do that. So decreasing, this is where I caught this, from -2 to -1, which is what we see from the values, so that's good. And then we're increasing all the way from -1 to 2, and it's good because our values confirm that. Okay, and then from 2 to 3, we are decreasing. So we're seeing that in our values. Okay, now concave up, concave down. When our function g prime is increasing, we're concave up. So we're concave up on this side of the axis, and when it's decreasing, when g prime is decreasing, we're concave down. So now we just want to put this all together and see if we can get a graph. So just try to really over-accentuate the concavity. So let's see, we're decreasing, concave up. Now at this point, we are going to be concave up, but increasing, okay? Now, we're going to continue increasing here, but notice it goes concave down. Okay, so concave down, and then finally, we're going to be decreasing here, and we're staying concave down. So, a little lumpy, but it gives us a pretty good graph. And let me point out that when we were just given g prime with one value, we did not have the level of accuracy we had that we have here, because we would start with that one point, and then from where it crosses the x-axis and things like that, we really was just a guess based on the shape. So that is it for integral defined functions graphically. Let me just summarize once again. The big thing here is when we're evaluating values of g, we draw a dotted line wherever that value is, dotted vertical line. As you move to the right, we're going to add the areas above, subtract the areas below like we always do, but when we move to the left, because that property is going to flip, these areas above will now be subtracted, the areas below will now be added, and then wherever that vertical line is where that original function is 0. So keep that in mind. And then of course right away we know that g prime is equal to f. That does not matter what that bottom limit is when we start answering those questions. Okay, so that is it for 4.4, the fundamental theory calculus.